Okay, hello everyone. Can everyone hear me and see me?
Yeah.
Okay, great. So welcome to the first problem session. And so let me begin with how I plan to run the problem session throughout this quarter. So in the problem session, I will show some sample problems that will involve techniques useful to the homework for that week. And then, so I'll probably run like 1 or 2 problem per week, and that you can expect the whole going through the problem would take about 30 minutes in the problem session. And then for the later half of this problem session, it's just like regular office hour. You can ask questions about anything on homework or on the problem I went through. Does that sound good? Okay, so can you guys see any share screen right now?
No.
No? Okay, let me try this again. Oh, and by the way, all the notes in the problem session will be uploaded to Canvas in the file directory. So I'll upload the file like right after the session ends. All right. And okay, so as I go through the problem, just feel free to interrupt me if you have any questions. Okay, so the problem I will be talking about. Sorry, I have to admit some other students into the. Okay, so the problem we will be talking about today is like it will involve techniques like converting the units, like for example, converting angular units to physical size units in astronomy. Also, we will talk about how to compare the magnitudes between 2 objects. Okay, so let's begin. All right. So first, if we want to measure the size of a galaxy, there are multiple ways we can do that. And there are some commonly used definition for a radius of a galaxy. And the example I'll be showing today is the radius at a surface brightness in B band. If the surface brightness in B band of a galaxy equals to 25 magnitude per arc second squared, then we will use that distance as the radius of that galaxy. So this thing is the surface brightness. Actually in B band. Okay, so so it's useful to know that surface brightness is independent of distance. So, it should be, because if we are going to use that for measuring the size of the galaxy, then it means it should be independent of distance, because like so that this radius should not change depending on the distance of the object, right? And we will show that. And the question is, sorry. So I should write that this is independent to distance. Okay, so let's start the question. So the question is, if we have a galaxy at, let's say, 10 megaparsec, the distance is 10 megaparsec, and how many suns, like this is the suns of our solar system, in a parsec square region will be equivalent to a surface brightness in B band of 25 magnitude per arc second squared. Okay, and so some information we have about the sun is, this is from table 1.4 in your textbook. Okay, I'm just trying to make the left column disappear.
Oh, excuse me? Could you scroll up really quick?
Yeah, sure.
Oh, thank you. I just need to get a picture.
Okay. Okay, so, okay, I can't make the left column disappear. Okay, so that's just, all right, so this is
Sorry, can you try expanding the screen by pressing those arrows at the top right-hand corner? See if
the
that does
top
anything.
right hand. Oh yeah, that works.
Yeah.
Thank you so much. Okay.
No problem.
So, okay, how do we think about this problem? So first, it's pretty clear that the surface brightness has a unit of magnitude per arcsec square, right? But we are putting suns in a parsec square region. So it's pretty obvious that we have to convert arcsecond to parsec, right? So this problem is basically asking if we are putting suns, lots of suns, in a parsec squared region. So many suns, and we don't know how many suns we should put in. And that surface brightness, that apparent magnitude in total for this region should be 25. The apparent magnitude should be 25 in total, right, in B band. Okay, so first, the first step, we should convert arcsecond to parsec. And then the second question is, we have to compare the magnitude between the suns, compare so we should, oh, sorry, I found that I haven't give you the conditions of the suns. So given by table 1.4, we have some information on the sun, which is the absolute magnitude in V band of 4.83 and the B minus V color of 0.65. Okay, so yeah, so the second step is to, since we have the absolute magnitude, but we want the apparent magnitude, right? So we have to convert the absolute magnitude in B band to apparent magnitude in B band, because that's where the surface brightness of 25 is defined, right? And then the third step would be compare between the apparent magnitude of the sun of one sun and multiple suns, right? And many suns. Okay, so let's start. So for the first step, how do we convert arcsecond to parsec? What is what does it mean by converting an angle to a physical size? So let's say here is our telescope, and okay, so I see something happening in the chat. Is it a question or you're just discussing? Okay, just feel free to type anything in the chat or just unmute yourself to ask questions. Okay, so to convert arcsecond to parsec. So when we observe, say this is our telescope, observe something very distant, right? So let's say the galaxy is here, and this is the size of the distance, right? And we don't know what is the actual size. So let's say the size is x, and the unit is parsec. So when we do observation in astronomy, the size is always in angles because of the angular resolution of our telescope. And so angle is basically a observational unit. So like when we observe the galaxy, here is the angle, right? But if we want to do anything like for a scientific purpose, we have to convert that into physical scale. All right, so since this is a very distant object, let's say the distance is d over here, we can use small angle approximation. So this means that x in parsec equal d times theta, right? And this theta should be in radian, and d should be like whatever units you have for x. All right. So we want to compare arcsecond to parsec. So let's see how many parsec is equivalent to 1 arcsec. Okay, so let's say if the theta is 1 arcsecond, and we would have to convert 1 arcsecond to radians, right? So 1 arcsecond is basically 1 over 3,600 degrees. And that is, to convert to radian, we multiply by pi over 180. And then we will get this magic number. So this number is really useful, and I will tell you why later. Okay, and then the distance. So the distance is already given by the question, right? So the distance for this example, the galaxy is 10 megaparsec, which is 10 to the 7 parsec. All right, so now we can calculate x, right? So x equal d theta and that's 10 to the 7th parsec times 1 over 206,265. And we will get 48.5 parsec. So this is the answer we want. This 48.5 parsec is equivalent to 1 arcsec for this galaxy. Okay, so now I'll tell you why this number, I mean 206,265, this is a very useful number worth memorizing, because for example, if we now want to convert 48.5 parsec to astronomical units AU, then what number would we got? So we know that we will use 1 parsec equal 206,265 AU. So if you check up the unit conversion between parsec and AU, you'll see 1 parsec equal this amount of AU. And you will see that, so 48.5 parsec would be 10 to the 7 AU, right? And you can see that 10 to the 7 is basically the distance of our galaxy in parsec, right? So it is same as the distance of our object in parsec. So why is this number the same? I believe you all learned about parallax in the lectures, right? Correct me if I'm wrong. So I'll give a brief review. So because of the parallax measurement, so sorry, this is the sun, and the definition of parsec is actually from the parallax measurement. So this is our Earth. So we know this distance here is 1 AU, right? And if we measure a star or any object far away, like we measure it 2 times, one time each when the Earth is on like one side of the sun. And we defined 1 parsec as the distance when we get an angle of 1 arcsecond right here. So if we observe 1 parsec, if we observe an object 1 parsec away and measure it by parallax, the angle here would be 1 arcsecond. So again, like if we use the small angle approximation, we have d equal x theta, right? So in this case, it would be 1 parsec, 1 AU equal 1 parsec times 1 arcsecond. But of course, we have to change this to radian. And as we just derived, to change 1 parsec, to change 1 arcsecond into radian, we got this 1 over 206,265, right? So that's how we get this relation. And so a useful thing to memorize is if we are observing an object with a distance d parsec. So if we, let's write it down. if observing object at d parsec, then we have like the 1 arcsecond we observe on that object would be equivalent to a physical scale of d AU. This is a very useful relation. So you can you don't need to always check up the conversion between units. You just have to memorize this, and then you can do the calculation really quick. Okay, so let me conclude for this part. So we just calculate that 1 arcsecond for a 10 megaparsec galaxy is equivalent to a physical scale of 48.5 parsec. And remember, the surface brightness unit is magnitude per arcsecond squared, right? So we actually want to convert arcsecond squared to parsec squared. So we have 1 arcsecond squared equivalent to 48.5 squared parsec squared, and that is about 2000 parsec squared. Okay, so this is the first part. We convert arcsecond squared to parsec squared. So any questions? If there's no question, I will proceed to the second part.
Quick question. If you scroll up a little bit.
Yeah.
Right there. Is that pi over 1 AU, or what is that?
Sorry?
Is that pi over 1 AU?
You mean here?
Yeah.
It's pi over 180.
Oh, okay.
Because
Okay.
180 degree is equivalent to pi, right? 1 in degree and 1 in radian. We want to convert degree to radian. Yeah.
Perfect. Thank you.
No problem. Okay, so the yeah.
Oh, sorry. Could you just go to the very bottom? I wasn't able to finish writing it.
Oh. Okay, so I will go on. So for the second part of this question, we will convert the absolute magnitude of sun into the apparent magnitude in B band, right? Okay, so let me rewrite the condition we have for sun again. We have MV equal 4.83 and V minus V equal 0.65 for sun. Okay, so with these two relations, it's obvious that we can first get the absolute magnitude in B band, right? So the absolute magnitude in V band would be that in V band plus B minus V, and that is 5.48. Okay, and then we want to convert this to the apparent magnitude. So apparently we have to use the distance modulus, which you will need to prove in the homework, right? This is equal 5 log d minus 5. Okay, and since we already have the distance, right, it's basically 10 to the 7th parsec. So remember, when you use distance modulus, the distance have to be in the unit of parsec. This is very important. Okay, so this is easy. 7 times 5, 35. So it's 30, right? And we know the absolute magnitude here. We just derive it, right? So in B band, it is 5.48. So we have the apparent magnitude of the sun in B band as 30 plus 5.48, right? Which is 35.48. Okay, so pretty trivial. And then any question for this part? Okay, so the third step.
We're actually.
Yeah.
No, I don't have a question anymore. Thank you.
Oh, okay. Great. So for the third step, we need to compare the apparent magnitude of n suns and one sun. So how do we compare apparent magnitude between two objects? So if you recall from the lecture on last Thursday, I believe, we have we can compare the apparent magnitude by using the relation with the flux, right? So it's something like this. And since now we are going to compare between one sun and n suns, we know if we have n suns, the flux would be n times more than a single sun, right? So we can write this equation like the total apparent magnitude of n suns minus a single sun would be negative 2.5 log f total over f sun, right? And since I just mentioned that this thing equals to n times the flux of a single sun, so this term inside the log is basically just n, right? Okay, so we have negative 2.5 log n. All right, so remember, we want to calculate n, right? We want to determine n, and so that this n number of suns will create a total magnitude of 25, right? So the total magnitude here should be 25. And then from the previous step, we just derive the magnitude from a single sun to be 35.48. Okay, so now we get n. So n equal 10 to the this is 25 minus 35.48 should be minus 10.48. Yep. Okay. So 10.48 over 2.5. And we will get this number. So this is n. If we want to create a surface brightness of 25 magnitude per 25 magnitude, we will need this number of suns. But remember, the question being asked is to create a surface brightness of 25 magnitude per arsec squared. So we still have to evaluate. write this down, to produce the surface brightness of 25. This is this number of suns in B band in this much parsec squared. So this is the equivalent to 1 arcsec squared we just derived. So that is equivalent to 6.6 suns per parsec squared, right? So yeah, so this is the final answer we get, 6.6. Any questions so far?
Yeah, could you remind me where we got 5.48?
5.48. You mean 5.48 or 10.48?
What's the equation that says MB plus MV's? Okay, scroll up a
Oh,
little
you
bit.
mean
Oh, okay, yeah, that's
here,
what it
right?
was. Yeah.
Yeah.
Okay, thank you, that was all.
Yeah, that's from the absolute magnitude. Okay, so another thing, remember I just said that this measurement, the size measurement of the galaxy should be independent to distance, right? So the example we show are for a galaxy at 10 megaparsec, right? But the final answer should be invariant, no matter which distance we have, we should get the same answer, right? So you can try that. So if let's use, okay, so here we assume distance equal 10 megaparsec, right? You can try if we modify the distance into 1 megaparsec, like how will the answer change? So I can give you some hint right now, and you can try it yourself in detailed calculation. So if we change the distance, there are just some part we need to modify, right? So like for example, when we convert arcsecond to parsec, this number here would be 10 to the 6th right now, right? Because it's now 1 order of magnitude lower in distance. And so we will get 4.85 right here. And so 1 arcsecond squared would be equivalent to 23.52 over here, right? Because we need, because this is squared, okay. And then we need to multiply the distance in the distance modulus, right? So now this thing is 10 to the 6th, and that would make this thing 25, right? And so this thing would be like 5 less than previous value. Okay, so yeah. So you can try with these number and see. At last you should get a value of. So this value here should be 100 times smaller. It should be something like this, and for this we just derive that it's 23.52. So you can see that since both the denominator and the denominator are like 100 times smaller. So it basically cancels out because both of them are proportional to distance squared. So if you calculate this, it is also, you will also get 6.6 suns per parsec squared. And so this thing is surface brightness is invariant with distance. Okay, you can try that after at home. Yeah. So this is the problem for today's problem session. So any questions?
Well, I had just one question about the conversion from arc seconds to parsecs.
Yeah.
So is it I guess I'm wondering, so like the part, like if you had this one galaxy, right, like the size wouldn't change if it was closer to you, it would the distance would be smaller, but then the would be more arc seconds kind of
Yes.
wide, right? Because it's closer, so that's why it doesn't matter. As one gets smaller, the other gets bigger.
Yeah, exactly. So if you look like this equation here, x equals d theta, basically if you have a smaller d, then you have a larger angle, right?
Yeah.
Yeah.
Okay. Is
yeah.
that like the same thing as you were just describing now? Going through the problem again, changing it?
Changing. You mean like changing the distance?
Yeah, like how you just adjusted everything, but it was the same density of suns. Is that because of that, or is that just a coincidence of how you set it up?
The relation you just mentioned, like smaller distance and corresponds to larger angle, that actually that is not related to so what I mentioned here is the surface brightness is invariant with distance, and so yeah, so that's a different
Oh, okay. That was about, okay.
yeah, but you can think of
Review that.
like so surface brightness, if you see the unit, you'll see the unit is the brightness per an area, right? And if your object is in different distance, then that area will change. So area is proportional to distance squared, right?
Yeah.
That is why it will cancel out, because both magnitude and because area is proportional to distance squared. So it's also somehow related to if you have a closer distance, then you will see the angle you see will be larger, but it's not directly related. Do you see
Okay.
what I mean? Yeah.
Yeah, I think so. Will you upload these notes so I could just kind of follow through that on my own? Like the edited numbers and everything.
Sorry, could you say that again?
Oh, sorry. Could you will these notes be uploaded at the end?
Yeah, I will
Okay,
upload
cool, yeah.
the note like after this session, and
Okay, thank you. I think I just need to follow through it on my own.
Yeah. No problem. So I will also have office hour tomorrow at the same time. So if you have questions on homework, you can ask either now or tomorrow at the same time.
Can I ask a problem about number 3 from the homework?
Number 3? Okay. Wait a second. Just let me open